Suppose f is a function from a to c, g is a function from b to c, and the sets a and b are disjoint. Okay, let's draw a picture of that. So we have a set a and a set b, which is disjoint from a, and another set c over here. And then we have a function f from a to c, and a function g from b to c. All right. Now earlier we proved that f union g is a function from a union b to c. Okay. So remember, functions f and g are relations, right? They're sets of ordered pairs, and so it makes sense to take the union of those sets. The way you can think about that is f is a bunch of arrows from elements here in a over to c, and g is a bunch of arrows from elements in b to elements in c, and then f union g is just the union of all those ordered pairs, or all those arrows. Okay, so we get a new function with a larger domain, a union b. Now suppose in addition that these two functions f and g are both one-to-one, prove that f union g is one-to-one if and only if the range of f and the range of g are disjoint. Okay, that's a mouthful. Well, it's an if and only if statement, so there are two directions, right? So first of all, we could suppose that f union g is one-to-one and prove that the ranges are disjoint. Okay, so that one would go by that direction would go by contradiction, right? Well, it could. So if you suppose that these are not disjoint, then you have some element, we'll call it c or c naught here in the set capital C, which is in the range of f and in the range of g. So what that means, because it's in the range of f, you have an element of a such that f of a is equal to c. And because c is in the range of g, you have an element b here in b such that g of b is equal to c. Okay, that's what it means for these ranges to not be disjoint. And while we know that f union g is one-to-one, and look, if this ordered pair AC is in F, it's also in F union G, right? And if this ordered pair BC is in G, then it's also in F union G. And so remember, F union G we know is a function. We have two different inputs in the set A union B, which have the same image under this function. Okay, and that tells us because we're assuming that f union g is one-to-one, that tells us that actually a is equal to b. That's a big equal sign. All right, but that's a contradiction, right? Because we're assuming that a and b are disjoint sets, and here we supposedly have an element that's in both. Okay, so let's work out that the direction of the proof, and then we'll come back and draw another picture for the other direction. For our givens, we have that both of these are functions and they're both one-to-one. A and b are disjoint, and f union g is a function from a union b to c. And we have this if and only if statement as our goal. So we're doing the forward direction, and we do direct proof. And we can write out the definition of what it means for these two to be disjoint, that there does not exist a c which is in both, right? And we'll do proof by contradiction, so we can assume there does exist a c in both. And existential instantiation will give us a c naught. We'll call it c naught here. You can call it c if you wanted to. A and b being disjoint gives us that definition. And f union g being one-to-one means if you take any x1 and x2 in the domain of that function, and if they have the same image, then they must be equal. Right? Now, c naught being in the range of f means there exists some a in the domain of f, which is capital A, which gets mapped to c naught by f. And similarly, c naught in the range of g means we have a b in b, which gets mapped to c naught by g. And a couple more existential instantiations give us that. And now that we have an a naught in the set A, we can do a universal instantiation there to get this, which remember came from the fact that a and b are disjoint. And another universal instantiation on a naught and b naught, which both are in a union b, right? So we get that, which was from f union g being one-to-one function. And okay, the disjoint thing gives us that, well, if a naught is in A, then it cannot be in B. However, a naught and b naught, which map to the same thing, because f union g is one-to-one, must be equal. And well, that's a contradiction, right? Because we have that a naught is not in B, b naught is, but they're equal. So either one of them is both in B and not in B. That's a contradiction. Okay, so that shows, that's written out in our proof over here. You can go ahead and read that through and match it up. And well, we still have the other direction, so let's give that a shot. Maybe we can try and draw a picture first. Let me get my A, B, and C up here again. Okay, and my functions f and g. All right, good. Now this time we're assuming that the range is a disjoint and trying to prove that it's one-to-one. If you want to prove something's one-to-one, you should take arbitrary elements. Oh, I just realized something. We take arbitrary elements of the set A union B, and I don't know whether they're in A or B. So actually what I'm going to do is just draw a single set A union B here as my domain of this function f union g, and then I have C over here. Okay. Then I have a function. I'll write the C up here. I have this new function f union g from union, not you. From there to there. Okay, good. And so to show that this is, to show this is one-to-one, which is my goal, I'm going to suppose I have a couple elements, x1 and x2, in the domain, and I'm going to suppose that they map to the same thing. Okay. Maybe I'll call it C. And then from that I have to show that x1 and x2 are equal. Okay. Well, what I'm assuming is that the range of f and the range of g are disjoint. All right. So this is where it gets a little bit tricky. So f union g of x1 is C. Right? What does that mean? That means the ordered pair x1 C is in that function f union g. And similarly, x2c is in there as well. Okay, so x2c is in f union g. Okay, now that means that these guys are either in f or they're in g, and I claim they have to be in the same one. Okay, because think, if this is in f, then that means that f of x1 is equal to C, right? And if the second thing is in G, that means G of x2, pardon my pen here, it's freezing a little bit, G of x2 is equal to C. Okay, hopefully you can read that. But then f of x1 equals G of x2, and that well, rather C, I should say that C is in the range of f and the range of g, right? Which would contradict our assumption that range of f and range of g are disjoint. So my point is that these ordered pairs must either both be in f or both in g, or else we contradict our assumption. Okay. So, oops. Okay. So what does that tell me? If they're both in f, then I can label these arrows with f. And I can use the fact that f is one-to-one to conclude that x1 is equal to x2, which is what I needed. Or if they're both in g, I can use the fact that g is one-to-one to conclude the same thing. Okay, so let's try to work that out. Direct proof. Definition of f union g being one-to-one. Prove the universal by letting x1 and x2 be arbitrary elements. And then a direct proof. Suppose the antecedent here and prove the consequent. Okay, and then here is the bit that I was trying to write down there in the a little while ago, that we have these being equal, and in fact, f union g of x1 must be either f of x1 or g of x1, and similarly this must be either f of x2 or g of x2. And because these ranges are disjoint, it has to be either both the f or both the g. Okay. So I'm saying either f of x1 equals f of x2 or g of x1 equals g of x2. So there's 2 or 3 steps kind of hidden there, but I didn't have space. So hopefully you can understand what happened there. And then, well, in either case, right, if you're in the f case, then you can use that f is 1-to-1 to conclude that x1 equals x2. Or if you're in the g case, you use that g is 1-to-1. Okay. So that actually showed up as 2 different cases over here in my proof. So that does it. And go ahead and read through this and make sure that you can match it up with what we did here.